morning, everyone. It is a great pleasure for me to introduce our guest speaker today. We'll be talking about the applications of quantum computing and how Quantinuum is working to make it all reality. Our speaker is a theoretical physicist and the Senior Quantum Evangelist at Quantinuum. He received his Ph.D. in theoretical physics from Columbia University and spent a decade and a half researching superstring theory and cosmology. Now, we are fortunate enough to have him speak to us today. Please join me in welcoming Dr. Mark Jackson.
Thank you, Arvin. So Arvin tells me you're all experts in quantum computing, and we can jump right to the really technical parts. So good. So it's a great pleasure to be here, talking to you, especially during Spirit Week. I understand. So I get to tell you about quantum computing. How many of you heard of it? I'm guessing everyone, because you're here in the quantum computing class. Good. And how many of you consider yourselves like pretty familiar with it? Like you program quantum computers and you follow things. That's okay. That's perfectly fine. So I'll tell you what quantum computing is and why we're going to all this trouble of doing it. So just a few months ago, this was Times covered. So quantum computing has been around for a while, but only now is it really becoming part of the mainstream. And I think you'll actually be shocked how close we are to having commercial applications of quantum computing. I did want to say something about my title, since Arvin mentioned. So that actually is my title, by the way, Senior Quantum Evangelist. I was a little weirded out when they first suggested this to me about 2 years ago, but in Greek it means bringer of the good news. And it kind of became a popular term in the 90s in tech, especially from Apple Computer. I do get some funny reactions when I say this to people, that this is my title. The weirdest reaction I had was last year. I was on a second date with a woman, and she told me that our child would be running for president, but how could they possibly do that with a father who had the job title Quantum Evangelist? So that would lead to shame. So there was no third date. So I first want to kind of tell you why we think about quantum computing and why we're going to this trouble. So about 200 years ago was invented the first computer, as we would call it. And this is what it looked like. It was invented by Charles Babbage in Cambridge. And I know this kind of looks like an old-fashioned typewriter, but it is actually conceptually identical to the computers that we have today, because it has switches, and these switches are either on or off. And of course here, these are mechanical switches, and you can see them, but they function only in the on or off mode. And in 200 years, we've obviously made a lot of progress. This is the laptop I'm running the presentation on. And it's slicker, it's faster, it's easier to use, but it's conceptually exactly the same. It's just that the switches now are called transistors, but they're still on or off. We use ones or zeros for everything in classical computing. So then you fast forward about 160 years, and it was this guy. Do you know who this is? I know it says this, but you all recognize him? So Richard Feynman, he was this very famous physicist. He won the Nobel Prize. He wrote some very colorful books, and he was thinking about certain problems, and he realized that normal classical computers would never be able to solve these problems. Even though computers get better every year, he was thinking about the scaling of them. And he realized that there were certain problems classical computers would never solve, and most of these were quantum mechanics types of problems. And so he said, well, if this is how nature thinks, this is how we should build computers. We should build a calculator based on quantum physics. And that was a wonderful suggestion, but 40 years ago, no one had the slightest clue how to actually do this. It was like suggesting something from Star Trek. And so for about 30 years, a lot of university groups worked on this, and there was sort of this joke that quantum computers are 10 years away for 30 years. They kept saying, yeah, we're working on it, but they didn't have it. So before I get to the next step, so here's what a quantum computer actually is. So as you are already familiar, I assume, so normal computers work with these ones and zeros, and you can think of this like a coin on a table, because the coin is either heads or tails. It's one or the other. There's nothing in between. But a quantum computer is like a coin spinning in space. It uses a thing called a qubit, a quantum bit. And the coin could happen to be heads or tails, but it's free to pick any orientation. And so in that way, you might kind of describe it as both heads and tails at the same time. And so this is how a quantum computer works. It uses these qubits, which can be ones and zeros at the same time. So the technical name for this is called superposition. This is the physics term that we use for the fact that it can be two things at once. And when you combine this with another concept in quantum physics called entanglement, which says that this qubit over here is correlating to this qubit over here. And this is a purely quantum effect. We can't explain this using classical physics. So when you combine these two ideas from quantum physics, you can actually represent a huge number of configurations at the same time. So why would we do this? Why would we go to the trouble of building a computer based on quantum physics? It's because we think that we will be able to use them for problems that we never ever could have hoped to have solved before. And a prime example is in chemistry, and this is actually what Feynman was thinking about when he suggested quantum computing. So on the upper left-hand corner, this is my favorite molecule. This is caffeine. And it's not a very large molecule. It's only 24 atoms. And we've known for about 100 years what the equations are that describe how the molecule behaves. So it's called a Schrödinger equation or a Hamiltonian. So again, for 100 years, we've known exactly what the equations are. And you could put them on a computer to solve, but it would be a very big computer. It would be almost the size of the planet. So in principle, you could do it. It would just not be very practical. But if you were to consider a bigger molecule, like penicillin shown here, it would actually require a computer the size of the universe. So even in principle, we could not solve that. And even this isn't a very large molecule. Like pharmaceutical companies, when they're talking about developing medicine, they're talking about molecules which are tens of thousands of atoms large. So obviously we couldn't even hope to do that. And so it's problems like this that we would like to tackle, but we wouldn't using normal computers. But on the right-hand side, you notice this is what a quantum computer would need, and it's a very modest number of qubits. It's only in the hundreds of qubits. And so this is why we're so excited about quantum computing. It's not just a faster computer, it's so much more powerful. We think that we'll be able to use it to solve problems that we couldn't have before. And it's not just chemistry, I'm using that as an example, but there are so many other things that quantum computing will affect. So I've shown a few here, and not just quantum computing, there's sort of these related fields of like quantum sensing and quantum communication, and they all use the same kind of basic ideas. So in the next few years, basically every area of science and technology will be affected by quantum fields somehow. So, so I mentioned for about 30 years, there were university groups working on this. And then around 2012, there were some breakthroughs. And researchers realized this might actually be a thing. We might actually be able to build a quantum computer. And so that's when the first companies were started. So some big corporations like Google and IBM and Honeywell, they formed quantum groups. And then there were a few startups. And so, you may or may not recognize some of the names here. So in 2012, this was the entire commercial quantum world. That was it. There were like 10 groups doing quantum computing. And so they continued to make progress. And then around 2019, there was a breakthrough in some sense that Google, they achieved what's called quantum supremacy. And I know that sounds very sinister, but what it means is that they found one example of something that a quantum computer could easily do that a normal computer could not do. And it was admittedly a very contrived, silly example. They specifically engineered this problem just so that a normal computer couldn't do it, but a quantum computer could. But at least this made people pay attention, that already the technology was advanced. There was one thing that a quantum computer could do that we couldn't otherwise. And so then people really started paying attention to this. And the past few years have been absolutely phenomenal. This is a subset of the commercial sector today. So this isn't even every company. These are some of the companies. So there are now hundreds of companies all over the world doing quantum computing. Some are doing hardware, some are doing software, some are doing the components, some are doing like job training, consulting. So there's this whole ecosystem of companies filling some need in the quantum world. And again, we're very, very early stages. So it's obviously going to change a lot over the next few years, but there is this whole ecosystem of companies now. So how do you build a quantum computer? What is it that we actually do? So even though that sounds very science fiction-y, we've actually built several of them. There's over 100 of them that I know of in the Western world, either from big corporations or startups or university groups. And these are two examples. So on the left is IBM's machine. So you'll notice this chandelier-like picture, like this was on the cover of Time. So this is an example of what's called superconducting technology. So this means when certain materials, when they get very, very cold and they're absolute zero, they have these special properties which allow them to conduct electricity perfectly. And you can use this to build these qubits, and that's what IBM and Google and a few other companies have done. And so, so that's what it looks like. The quantum computer is actually a small chip at the bottom of the chandelier. But the rest of the thing, it's all needed to control the chip, because you have to have wires go in to tell it what to do. And then you'll notice those white cylinders in the background, those are filled with liquid helium, and that's what you lower the chandelier in. So that's why you don't actually get to see it when you're operating. And so, so that's one example. And then another example is the technology that we use at Quantinuum. It actually uses, it's called ion trap technology. So an ion, as you probably know, it's an atom which has extra or is deficient in charge. So it's not balanced, right? So we have these ions, we use a terbium, if you're curious, and we use lasers to control them. So, so it's a big tabletop-sized computer, and we have this vacuum chamber, so there's nothing in there except the ions, and then we use lasers to push them around. We actually physically move them and change their value. And so I'll explain more about that in a second. So this is what it actually looks like. So that's an ion in our machine, and we use the lasers to change the value, and we move it around. So it's shuttling around. So that's one qubit, but of course the interesting thing happens when you get many qubits. So they're each doing their thing, and then when you want them to interact, that's the entanglement. When you get them physically next to each other and you zap them together, that's the entanglement. And so a quantum computer will have dozens or hundreds, or at some point maybe even millions of these qubits doing this very sophisticated choreography all together to run your program. So, so as I mentioned, there's over 100 of them in the world that I know of, and there's many technologies. Every technology has advantages and disadvantages. There's no one perfect technology. There's a reason that different groups are doing each of these. If you ask me which is the winner, I honestly wouldn't be able to tell you. Ours is very promising, but it could be that other technologies are better for specific problems. And so there will probably be several different technologies that end up doing this. What do you think the record is right now for the most number of qubits? How many think? So how many of you think it's like 10? 10 or more, let's say that. 10 or more, okay. How many of you think it's 100 or more? How many of you think it's 1,000 or more? How many of you think it's a million? It's not. So right now the record is 433. So IBM, using this superconducting technology, so it's 433, and in December they will very likely announce 1,000. They've already kind of told us this. So, so that's where we are today, but there's a big asterisk there that I should have written. Just the qubit count alone doesn't tell you how powerful the quantum computer is, because these qubits, these are physical objects, and they're very fragile, and the quantum world is very fragile. If you've watched Marvel movies, you know that. So you have to include the error rate in this. And it turns out that the superconducting technology, an advantage is that you can have lots of qubits, but the disadvantage is that the error rate is still pretty high. And so actually we at Quantinuum, we have fewer qubits, we have 32 right now, but the error rate is much, much lower, like 100 times lower, and it turns out that's actually better when you think about how powerful the quantum computer is. So, so ours is about 1,000 times more powerful than IBM's, for example. So how many of you have heard of Moore's Law? That most of you, yeah. So, so decades ago, Gordon Moore, he founded Intel. He noticed that computers got powerful every year. In fact, it was doubling every 18 months, I think, is roughly, right? And that's held amazingly consistent for decades. And that's why computers today are so powerful. So if you plot Moore's Law compared to the progress that we make in quantum computing, so you notice this is on a logarithmic axis there, so the lines look straight, but that's exponential progress, plotted linearly. Quantum is so much faster than that. So quantum actually has increased by about a 10x increase every year. And so it shows that's how much faster it is compared to Moore's Law. And so this is why quantum computers today are so much more powerful than just a few years ago. And based on this, we think in about 1 to 2 years, we will have commercial applications. So I talked about kind of silly contrived examples a few years ago, but we're already starting to do things which are actually interesting. The companies would pay money to solve. And so we're actually very close to having quantum be a real thing. I'll skip that in interest of time. So how do you program a quantum computer? It actually kind of looks like this. And I know this looks very silly, like a child's game or something, but this is what a real quantum program looks like. Every horizontal line is a qubit, and you read it from left to right. So they get initialized into the 0 configuration, just like a bit. So they're 0 to begin with, and then you apply these different operations on them. So you're changing the value of the qubit, sometimes just the qubit by itself, and sometimes you're saying, whatever the value of this qubit is, do something to this other qubit, even if I don't get to know what it is. And so you do all these complicated operations, doing the superpositions and the entanglements, and then at the very end, you'll notice those measurement boxes. So when you measure a qubit, you force it to choose 0 or 1. So up until then, it can be in this weird quantum state, but at the very end, when you measure it, you're forcing it to choose, and that will be the answer, 0 or 1. So each qubit at the end will produce that as the answer, and that's the output. So I know it seems kind of funny, you do all this complicated quantum stuff, but the output of a quantum program is still digital. It's still just ones and zeros. And what's more, it's that because it's quantum physics, you actually can't predict exactly what the outcome will be. It will actually be probabilistic. So there's some probability that the qubit will be 0, some probability that it will be 1, and you actually don't know the final answer. So often we run a quantum program many times, like 1,000 times, and we look at the distribution of the results, because just running it once doesn't really tell you very much. So why do we do this? What good is it? Why are we building them? So these are some of the applications that we've already thought of. So I mentioned chemistry, for example. So things like machine learning and optimization are prime examples of things that quantum computers are really good at. You might have also heard about cybersecurity, that there's a close relationship between quantum computing and cybersecurity. Yeah, and there absolutely is, and I'll explain more in a second. So finance, I know this doesn't sound very interesting to you, but there's a lot of banks that are very interested in this because they do all this trading. They buy and sell stocks, and they write computer programs to try to guess what the stocks are going to do, and they can buy and sell accordingly. So it turns out that the mathematics behind this is something called Monte Carlo. Have you heard of this or no? Yeah? Some of you actually, okay, fantastic. So it turns out there's a quantum Monte Carlo algorithm, which is quadratically faster than the normal Monte Carlo algorithm, which means that you would get the same level of accuracy running 1,000 simulations on a quantum computer as you would with 1,000,000 simulations on a normal computer. So obviously a lot of banks are very interested in this because if they can more accurately predict what a stock is going to do, that would be worth a lot of money to them. So there's a lot of interest from financial groups. There's also things like using machine learning. Unfortunately, in today's society, there's a lot of fraud, especially because a lot of transactions are online. And so there's a lot of work that goes into trying to figure out what are the legitimate transactions and what are the fraudulent ones. And we think that quantum computing could help a lot with that. How many of you have used Alexa or Siri or chatbots? Yeah, I assume everyone here has done this. So that the technical name for that is called natural language processing. It's the way that computers, they take the words that we say or we type and they figure out why we're using those words, why we put them into sentences and what we mean by this. And it turns out there's a quantum natural language processing. And so the mathematics behind this actually very naturally translates into quantum computing. And so there's an effort to develop things like this that can be used for a quantum version of Alexa or Siri. So I talked about chemistry as one of the prime applications already. And this sounds really funny, but if there's one problem that we would like to solve in chemistry, it's actually fertilizer. And I know that's funny, but the reason for this is about 2% of the world's energy supply goes into making fertilizer. And it's a very inefficient process. It was invented about 150 years ago, and we haven't improved on it much since. And it costs a lot of energy, it's bad for the environment, it's very expensive. And we know that bacteria are much better at doing this than we are, we just don't really know how they do it. It has something to do with this molecule, called Fumoko, something to do with this interaction. So we would like to model this interaction using a quantum computer to better understand it, and then maybe we could make fertilizer production more efficient. And so there were some estimates done, how big would the quantum computer need to be to do this? And Right now, it's out of our scope, but in a few years, this actually might be feasible. Probably not in 2 years, but in maybe 10 or 20, we actually might be able to have an improved process for doing this because of quantum computing. My personal favorite application is with the pharmaceutical industry. So, how long and how expensive do you think it takes for a pharmaceutical company to develop a drug? So I was shocked when I first learned this.
5 years?
So it's actually about 10 years, and it costs about $1 billion. So for some drug that goes on the market, it takes that much time and money for them to do this. And they use computers in the beginning. They can kind of get rough estimates of what the promising medicines are, but only very kind of order of magnitude type guesses. Then they synthesize all the possible drugs that might work, and then they do clinical trials. They actually just start giving it to people, and they see what happens. And that's obviously risky, and it takes a lot of time and money. And the best that they could hope for is that a medicine will help most people, and the side effects won't be too bad for most people. And so if pharmaceutical companies, if they could use a quantum computer at the early stages, then they could more quickly hone in on the promising drugs and better serve the population as a whole. And then there's this dream that maybe we could even do personalized medicine. So we could actually develop a drug just for you based on your genetics to maximize the effect and minimize the side effects. And so again, this won't happen in the next 1 or 2 years, but eventually this is where we're headed, that pharmaceutical companies could do things like this using quantum computers. These are a few things that we're actually working on right now. Carbon capture, this is a potential drug for Alzheimer's that we've been studying. So we're already starting to look at real world applications in chemistry. I will skip those. So cybersecurity. So yes, I've kind of noticed the one thing that people know about quantum computing is that it has something to do with hacking. And that's true. There is a good reason for that. And here's the reason. So about 60 years ago, they were developing the standards for cybersecurity. And so when they developed these encryption formulas, what happened is they used these formulas, which are purposely very complicated, so that when you send your credit card numbers to Amazon or whoever, your computer applies a very complicated formula and transmits that, and then Amazon or whoever, they use a key to undo the formula. And most of the time this works really well. When you hear about hacking, it's usually because of a human error, not because the formula was directly undone. And so most of the time it works very well, but 60 years ago, they weren't thinking about quantum computing, which is understandable because no one had even thought of such a thing. So it turns out that the formulas that they chose all those years ago are vulnerable to quantum computing. And here's why they're vulnerable. So the formulas are based on factoring numbers. You might have realized at some point in your life that it's very easy to multiply numbers together, but it's very difficult to do the inverse of that. If I give you two numbers, I know that you can multiply them together, and if I make the numbers about twice as big, it will take you about twice as long, but that's it. The method is identical. But if I give you a big number and I ask, what are the two prime numbers that I would need to multiply together to get that big number? You would basically have to just go through all the primes and check. There's no fast way to do it. No one has ever found an efficient way to do that. And so that's how encryption works most of the time. It's sort of this one-way door mathematically. So it turns out that quantum computers are very good at factoring. And this was realized about 25 years ago. This professor at MIT was thinking about this, and even though no one had built a quantum computer yet, he said, well, what if someone did build one? Here's how a quantum computer would behave, and he worked out the recipe for how a quantum computer would factor numbers quickly. And this was it's called Shor's algorithm, if you're curious, S-H-O-R. This was academically interesting, but no one saw this as a very serious threat because, again, there were no quantum computers. Now people see this as a very serious threat. Quantum computers aren't able to hack these today, but in a few years they might be able to. And just to underscore how big of a threat it is, about 99% of the encryption on the internet is based on formulas that are hackable in quantum computers. So that means that anyone with a sufficiently powerful quantum computer could just read your mail or access your bank account or do anything that you would not want them to do. So fortunately, obviously, computer scientists and physicists and people have been paying attention. They've been aware of this threat. And so there's actually a contest going on right now by this American government agency they've asked people to submit new ideas for encryption formulas based on mathematics that we don't think quantum computers can hack. So a few years ago, they started this contest. There were over 100 submissions. People did their best. They investigated it. They did their best to hack things. Last summer, there were 4 winners announced, and then within a few days, 2 of them were hacked. So there's a lot more work that needs to be done clearly. Actually, I think just a few days ago, just 1 month ago, they said that, no, wait, we really have some winners this time. But obviously, people will need to check this more carefully. And you might use Signal, the messaging app. Just a few days ago, they announced that they're going to be using this it's called post-quantum encryption algorithms. So this is already starting to be used in the real world. I'll skip that. So that's how quantum computing can be used for hacking. Quantum computing can also be used to prevent hacking. And the coolest way that this happens is something called quantum key distribution. And this is when you're sending photons by themselves, either through fiber optics or with lasers. And actually, China has already launched a quantum satellite. It's up in space right now. About 7 years ago, they launched a satellite. And it uses lasers and entangled photons to do this. So that's already been done. And I'll finish with this. So you might ask, well, how could this prevent hacking? So the way that this happens is, so suppose you had entangled qubits. So remember, entanglement means they're correlated. Whatever one qubit is, the other one is, even if they're random, even if you don't know what they are, at least they're random together. So Alice and Bob are the 2 people that want to communicate. So they do this calibration check first. So Alice measures her qubit and doesn't tell Bob what she's doing, and Bob measures his qubits and doesn't tell Alice what he's doing. So they do this calibration and they get their results, and if they're measuring their qubits, their photons, in the same direction, they should always get the same answer, 100% of the time, because of this entanglement. And if that's true, then they can go ahead and communicate, and it's all good. Hi, everyone. But now we do this using some sort of eavesdropper. So the eavesdropper is trying to be really sneaky. So the eavesdropper is intercepting the qubit, measuring it, and then replacing it, right? Because they don't want to be detected. So if this were classical physics, this is the perfect crime. We would never be able to detect it if Eve were really good at doing this. But you'll notice that because Eve has done this measurement, she's destroyed the entanglement. And so now it is different. So Alice and Bob, they do their calibration checks, they do their measurements, and then when they compare notes, some fraction of the time, even if they've measured in the same direction, they are getting different answers. So they know that something funny has been going on. They have mathematical evidence that there's some sort of eavesdropping or tampering or something. And so then Alice and Bob can say, okay, this isn't a secure channel, we'll do it somewhere else. So this is a way of using quantum physics to protect our communication. And so obviously, not everyone will be using this personally, but government agencies and banks and communications companies, they will be using this, either again with fiber optics or with lasers. So I know this probably doesn't sound very interesting to you, but a huge amount of money is going into this. So we think that the market potential, right now it's in the hundreds of billions. We think eventually it will be in the trillions. So this is why all these companies are starting, they're investing and starting all these companies. This is going to be huge. This is a chart showing how much investment has gone into quantum computing. So you'll notice before 2012 there was nothing, and then it kind of slowly ramped up, and the past 2 years it's just exploded, and this year will be even higher than that. So there's so much going on. So yeah, that's governments. So I'll just say a few words. So you are in exactly the right place at the right time. So it is your generation that's going to be doing all the cool stuff in quantum computing. It's sort of like in the early days of computers. You've probably seen historic photos of computers when they were yay big and they had wires sticking out that thing. That's kind of where we are now. So it will be decades of progress in quantum computing. And so it's you guys that will be doing this. And I've talked about some of the applications of quantum computing, but these are kind of the obvious things. These are things that we would want to do with our normal computer. But the truth is, it's probably going to be someone your age who thinks of the killer app, because we haven't even thought of it yet. Often it's not until the technology is already there that we kind of realize what we should do with it. So, yeah, this is, I think, going to be the coolest thing that you could ever work in. So anyway, I hope we have a few more minutes so I can answer questions if you'd like to ask me.
Well,
I think this kind of follows up on what you were just saying, but now that quantum computing is like rapidly growing, and you're saying it's increasing like 10 times, even more than classical Moore's law. But what can we as like students do, whether it's in high school or later in college, to maybe like prepare for the future, set ourselves up for success?
Yeah. So until a few years ago, there wasn't really much you could do outside of a university lab, unfortunately. But now there's actually so much stuff available for free on the internet. So first, if you want to set yourself up,
That's right. It's time to go to class.
So take all the math and science that you can. Obviously, you do well in them. Just go to good college, do all this. But you can also do projects. IBM has actually put a lot of stuff online. Some of their computers are available for free. There's a lot of online courses and things, and a lot of universities are offering quantum computing certificates and degrees now. So there is a lot of stuff.
Thank you.
All right, folks, we need to